Now, aldehydes may be prepared by heating a mixture of dry salts of calcium formate and a calcium salt of any other acids. So calcium formate is a must, and this is calcium formate HCOOCaOCOH. So this is calcium formate, and then you take a homologue of calcium formate, and this is calcium acetate because CH3COOH is acetic acid. And since calcium is divalent, we have two acetate groups. On heating, the process is called dry distillation. Anyway, it is heating. Then the CH3 part of the other acid combines with the HCO part of calcium formate. So we get CH3 bonded to this carbon and H double bond. So this forms the aldehyde group. So CH3 bonded to CHO group. Now here also CH3 bonded to CHO group, and the resulting part of these molecules contain 2 calcium, 2 carbons, and 4 plus 2, 6 oxygen atoms. So the product will be calcium carbonate, and we get acetaldehyde as the product. We can take another acid, say calcium propionate. Then the ethyl group of the acid part will combine with the CHO to form propionaldehydes, and so on. Now, a similar method can be used for the preparation of ketones. Now, for this, the calcium salt alone is heated. A calcium salt other than calcium formate alone is heated, and there the CH3 part combines with the COCH3. The valency over this CH3 combines with the valency over this C. So we get CH3 COCH3, that is acetone. And the remaining portion is calcium carbonate. So 2 simple methods for preparing aldehydes and ketones. Now coming to other methods of preparation of ketones. Now methyl ketones may be prepared by treating an aldehyde with diazomethane. Now azo indicates nitrogen, diazo indicates 2 nitrogen, and methane CH4. Diazo group is divalent, so you replace 2 H atoms from methane CH4, it becomes CH2, then connect it to diazo, that is N2. So CH2 N2 is diazomethane. So that CH3CHO is converted to the methyl ketone CH3COCH3, where the CH2 combines with H and connects to this carbon, and N2 is removed as nitrogen gas. Now diazomethane is having a number of canonical structures. One such structure is this one. Tetraval nitrogen is positive and dival nitrogen is negative. Now negative charge means a lone pair present definitely on this nitrogen, so that lone pair becomes a bond pair here. Then simultaneously this bond polarizes in this direction, so that the positive charge over nitrogen is unaffected. There is gain and loss, so no change in charge. CH2 becomes CH2 negative, single bond N positive, triple bond N. The charge over this nitrogen is getting neutralized. Now that canonical structure where CS2 is negative attacks the carbonyl group and CO group polarizes like this. So we get CS2 connected to the carbonyl group, oxygen becomes negative, N positive to bond N, and then there is H is shown here. Now here this H with the bonding pair of electrons shown here. So complete bond and atom migrates to CS2 with the simultaneous removal of this pair of electron over nitrogen. So when this electron pair is absorbed, taken up by positive nitrogen, its charge is getting neutralized and we get N2 gas molecule. And this pi bond, this lone pair becomes a pi bond here. So from negative charge we show an arrow like this. This arrow indicates that a lone pair is becoming a bond pair, especially a pi bond. And when this hydrogen with the bonding electron pair is removed, carbon gains a positive charge. The valency of carbon is now 3. It becomes 4 when this pair of electron becomes a bond pair. So valency of carbon is maintained. And here also when this hydrogen with the bonding electron pair moves to this carbon, the valency of this carbon becomes 5. And when this pair of electron is removed by nitrogen, the valency of this carbon again becomes 4 and we get acetone, so the corresponding methyl ketone. In fact, any aldehyde on reaction with the CS2N2, for example RCHO, we get RCOCH3. So that is a method for preparation of methyl ketones, and again a conversion method. How will you convert acetaldehyde to acetone? There is only one path, a one-step reaction, that is reaction with the diazomethane. Now from acid chlorides can be converted to ketones by treating it with the dialkyl cadmium. Now dimethyl cadmium, so cadmium connected to two alkyl groups. Then acid chloride is CS3COCl, one example, acetyl chlorides. Generally we can write RCOCl and R2CD. Here CS3COCl is taken, acetyl chloride it is called, and this is called dimethyl cadmium. Now this CS3CO portion breakage occurs here, and here breakage occurs, and two CS3CO portion combine with the CS3 and CS3 giving CS3CO CS3, two acetone molecules, and this chlorine combines with the cadmium, so this bond also gets broken. Cadmium combines with the two chlorines from two acetyl chloride producing cadmium chloride. Now dialkyl cadmium is prepared by reaction between a Grignard reagent and cadmium chloride. Here two molecules of methyl magnesium chloride reacts with the CdCl2, that is cadmium chloride. Then CdCS3 twice is formed, and the chlorine here combines with the MgCl, 2MgCl plus Cl2 giving 2MgCl2. So simple equation. So Grignard reagent reacting with the cadmium chloride, methylation reaction here. Methyl magnesium chloride plus CdCl2 giving CS3 twice Cd, and this cadmium compound, dialkyl cadmium compound, can react with the acid chloride producing ketone and cadmium chloride. So that is the production of ketone from acid chloride. And for production of acid aldehyde from acid chloride, we use hydrogen, palladium, support bond barium sulfate acting as a position, and that particular reaction is called Rosenmund reduction. That you should know. It is important. Heme reactions are important. Then some more examples are given. CS3, CS2, COCl plus C2H5 twice CD. We get CS3, CS2, CO, C2H5, 2 molecules, then CdCl2, then CS3, CS2, COCl plus CS3 twice CD. We get CS3, CS2, CO, CS3, 2 molecules plus CdCl2. So simple examples, easy to understand. From nitriles or cyanides. Nitriles are also called cyanides. Then a nitrile is treated with a Grignard reagent and then hydrolyzed. For example, CH3C triple bond N. Grignard reagent splits into Mg positive and CH3CH2 negative. Now this negative part goes to the carbon because CN bond polarizes in this direction, and the MgBr connects to this nitrogen. There is a double bond, so CH3C connected to CH2CH3, double bond N connected to MgBr, and we get such a structure which on hydrolysis this portion gets hydrolyzed as shown here. Now nitrogen is the negative part and H positive from water connects to nitrogen, and MgOH is removed and we get an imine structure. And this imine on further hydrolysis, again right hydrolysis, breakage of the complete bonds, and nitrogen being the negative part, 2 H positive atoms combine with nitrogen forming ammonia, and a C double bond O is formed. So we can show these hydrolysis in the single step. Here hydrolysis occurs and here hydrolysis occurs. Here H2O and here HOH. Then NS3 is formed and then CH3CO. So here it is written CS2, CS3, and here only CS3. So you have to write it as CS2, CS3, and here also CS2, CS3, and here also CS2, CS3, because we are taking this ethyl magnesium bromide as the ingredient. So correction CS2, CS3, CS2, CS3, and CS2, CS3. So this is we can say 1, 2, 3, 4. So it's a butanone, 2 butanone, or we can write the name as butan 2 on. So both names are possible. So that is from nitriles or cyanides. First of all, reaction with the Grignard reagent, then carbon connected to the alkyl part of Grignard reagent, hydrolysis, 2 portions are getting hydrolyzed, and MgBr portion getting hydrolyzed to NH, and imine structure is formed first. Is on further hydrolysis, we get the ketonic structure and ammonia. And for hydrolysis, we can use acid as the catalyst. If acid is the catalyst, then ammonia will be reacting with acid, producing ammonium salt and so on. So less important. Then coming to the physical properties of aldehydes and ketones. Now the boiling point of aldehydes and ketones are higher than those of either having same or nearly same molecular mass, because in aldehyde or ketone the carbonyl group is undergoing resonance to get a dipolar structure, so that the carbonyl group is more polar than the polarity of ethers. So aldehydes and ketones are more polar due to resonance, we can say. So there is greater extent of negative charge over the oxygen atom. This is a ketone. Then the R groups can exert their plus psi effects. So there are two alkyl groups in ketones exerting their plus effect, so that there is a greater push of electron density towards the oxygen, so that delta negative charge here will be higher than the delta negative charge here. When we compare a ketone and an aldehyde having nearly same or same molecular mass. For example, say acetone, CH3, CO, CH3, and an aldehyde having similar same molecular mass is propionaldehyde. So for propionaldehyde, the dipole moment is 2.57, whereas for acetone it is 2.88. So acetone has a higher dipole moment. Why? Because the inductive effect of two alkyl groups push the electron density towards the carbon and then towards the oxygen atom, so that delta negative charge will be higher here, and the magnitude of this delta negative will be the sum of the delta positive values taken together and its magnitude. So here we have to take the delta positive value of R, this R and this carbon, and you add all these delta values, and its magnitude will be the same as this magnitude of delta negative, and that magnitude is higher than the magnitude here. Means in the case of acetone and say propionaldehydes, the magnitude of delta negative charge over oxygen atom will be higher than that in the case of propionaldehyde, so that dipole moment will be higher, and higher the dipole moment, higher is the extent of attraction, that is dipole attraction, and higher is the association, and higher is the tendency towards liquid state, and so higher is the boiling point. So acetone will be having a higher boiling point than acetaldehyde. Of course, acetone is having a higher boiling point than acetaldehyde, but their molecular weights are not comparable. Acetone has a higher molecular weight, but the molecular weight of propionaldehyde and acetone are same, and their boiling point of propionaldehyde is 49 degrees Celsius, whereas that of acetone is 56 degrees Celsius, and that is due to the higher dipole moment and higher dipole attraction, higher association, so tendency towards liquid state is higher, and so the boiling point is higher. So generally we can say aldehydes and ketones having same or nearly same molecular mass, when compared, always the ketone possesses a higher boiling point and a higher dipole moment. Now coming to the types of reactions of aldehydes and ketones. Aldehydes and ketones are considered together because they possess the common group, that is C double bond O group, that is carbonyl group. Now here this carbon is sp2 hybridized, and R and R dash. R represent an alkyl group and R dash can be an alkyl or hydrogen. If R dash is hydrogen, the compound is an aldehyde, and if R dash is an alkyl group, the compound is a ketone. Now this carbon is sp2 hybridized. So that the carbon, oxygen and R dash will lie on this plane. Now the pi bond between carbon and oxygen, the orbitals over carbon and oxygen will be parallel to each other and will be perpendicular to the plane of this paper. The nucleophile has to attack from a plane perpendicular to the plane of the aldehyde or ketone molecule because it has to form a sigma bond with the p orbital over carbon, because when nucleophile with its bonding electron pair approaches or attracts or attacks this carbonyl compound, comes near this carbon, then this pair of electron in the pi bond is shifting entirely into the orbital of oxygen atom, and the carbon orbital becomes vacant, and then this filled orbital over the nucleophile overlaps the vacant orbital over the carbon, and now nucleophile, if possesses a negative charge, then the positive charge obtained by removing this pair of electron into this orbital will be neutralized, and we get this structure, and that is a slow process. So that is the rate determining step, and here we had the carbon in the sp3 hybridized state. So that only R1, R dash, R and O minus touches the plane. The carbon is above the plane and nucleophile is perpendicularly above the plane. Now then an H positive gets added to O negative by a faster step, and we get the product. Now here the significance of this wedges, that is complete fully shaded wedge and a broken wedge is shown. That only means that this R group directs towards us and this R dash group directs away from us. But when they are placed on a plane, R dash, R and OH, here OH will touch the plane. This doesn't mean that this wedged, dashed wedge or a broken wedge is below the plane. It is in the same plane as R and OH. Now that is the reaction. Nucleophile approaches from a side perpendicular to the plane of the molecule so as to form a sigma bond with the pi bond, because the pi orbitals are perpendicular to this plane. So nucleophile also has to approach from a perpendicular direction to this plane containing this molecule. So that is the mechanism for nucleophilic addition. Now aldehydes are more reactive than ketones for two reasons. One is a steric reason, that is an aldehyde that is R dash is H. When nucleophile approaches from this side, this R group can repel this nucleophile where H is very small, so the repulsion between H and the incoming nucleophile is negligible. So only one steric repulsion is felt by this nucleophile when it is an aldehyde. And when it's a ketone, R dash is an alkyl group, both these alkyl groups can repel the nucleophile. So in the case of a ketone, steric repulsion is greater than aldehyde. Now again, the nucleophile with a negative charge is seeking a positive center, that is carbon. So the amount of positive charge, it will be partial positive charge. So the amount of partial positive charge over this carbon decides the speed of attack of nucleophile or rate of reaction. Now greater the positive charge, higher will be the speed of the reaction, speed of attack of nucleophile. But if it is a ketone, then R groups show plus I effect. That means the electron pair in these bonds are more shifted towards this carbonyl carbon, so that its partial positive charge is getting diminished. So when we compare the partial positive charges of the carbonyl carbon in an aldehyde and in a ketone having the same or nearly same molecular mass, it is found that it is in the aldehyde the partial positive charge is higher. So aldehyde has got two advantages. It exerts lesser steric repulsion to the nucleophile, and it decreases the positive charge lesser than the ketone, corresponding ketone, means ketone having the same molecular mass or nearly same molecular mass. So two advantages for aldehydes, so that aldehydes react more easily towards nucleophilic substitution compared to ketones. So the two reasons are, one is steric and the other is inductive effect. So plus effect of two alkyl groups in ketones will greatly reduce the partial positive charge over the carbonyl carbon, so that nucleophile will show a lesser tendency for attack over the carbonyl carbon. And again, the two alkyl groups of ketones will exert more steric repulsion towards the nucleophile than aldehydes. So aldehydes usually react faster than ketones in nucleophilic reactions, and these reactions are called nucleophilic addition reactions because the double bond is getting saturated by the nucleophilic reaction. So nucleophilic addition of HCN, hydrocyanic acid, it's a weak acid, but cyanide is a good nucleophile. So to produce cyanide ions, free cyanide ions, the reaction is conducted in a base, so that H positive from HCN is removed as water molecule, and the Cn negative is released, and Cn negative attacks the carbonyl carbon. Cn negative is here the nucleophile. So Cn negative attacks the carbonyl carbon, and we get O negative, Cn the addition product. And then it's a reversible reaction. O negative can return back to the C double bond O state where Cn negative is removed, and we get back the aldehyde or ketone. Then this reacts with H positive to produce OH, and again this reaction is also reversible because cyanide group is showing a very high minus effect, so that this OH group is made slightly acidic in character than usual alcohol. So removal of H positive from this OH group is possible, and when OH group removes H positive, we get back this species. So this is acidic in the sense cyanide exerts a strong minus I effect. Now cyanhydrin, the product is called cyanhydrin, and if we are taking acetaldehydes, then we are getting acetaldehyde cyanhydrin, the nucleophilic addition product. Now here it is said that propanone, that is acetone, then butanone, there is only one butanone, that is 2-butanone, CH3, CO, CH2, CH3. Only one isomer for butanone. Then pentanthreone, that we can write easily the structure, but pinacolone, we are not familiar with this one. And pinacolone is CH3, CO, C, CH3, CH3, CH3. Again call it a 3-butyl methyl ketone pinacolone. It is said that these compounds, that is acetone, butanone, pentanthreone and pinacolone, only gives anhydrins. The reason is not given, maybe steric or electronic factors, but it is found that only these 4 ketones can give a cyanhydrin. Now addition of sodium hydrogen sulfide or sodium bisulfide, that is NaHSO3. Now the HSO3 group bisulfite group is given here as double bond O OH SO3H. It is negative, so that sulfur is carrying the negative charge and Na positive. Then this CO bond polarizes or ionizes like this, so that Na positive gets connected to O negative and SO3H group connects to this carbon through this sulfur. Now SO3H group contain an OH group. Now when this OH group ionizes as H positive and O negative, this negative charge may be delocalized over the other parts of the molecule as double bond O. So resonance is possible when OH group ionizes, so that the corresponding anion is stabilized by resonance. Hence we say OH group is acidic. And here we have O minus Na positive, which is the sodium salt of an alcohol, and alcohols are less acidic, means this OH group is less acidic than this OH group, because O minus cannot be stabilized by resonance. So when the salt of such a weak acid is treated with a strong acid, what happens is that this H goes to the position of Na and this Na comes here. So a strong acid can displace the weak acid from its salt. That happens here. A strong acid can displace the weak acid OH here alcohol from its salt. So that happens here. So we get SO3H ONA first, which easily reverses to SO3Na and OH. So this is bisulfite addition compound, and this compound is a salt because it exists as Na positive and SO3 negative, and the salt is soluble in water. So that is bisulfite addition compound. Since SO3H group is a bulky group, ketones are less reactive towards the reagents. So that is one disadvantage. That is, with ketones, the reaction is very slow or cannot happen easily, or ultimately stops with the ketones because of the bulky nature of steric repulsion of the bulky SO3H group. So the equilibrium, it is said that is far in the reverse direction, in this direction, than in the forward direction when we take ketones as a starting production. So ketones are less reactive towards bisulfite. That is the observation. Then the addition product is water soluble because it is a salt. It can be converted back to the carbonyl compound by treating it with dilute acid. So bisulfite addition compound can be converted back to the carbonyl, that is ketone or aldehyde, by reacting with the dilute acid. On reaction with the dilute acid, hydrolysis occurs. HOH addition, here S becomes negative and H positive gets connected, and OH connects to this carbon. We get NaHSO3 sodium hydrogen sulfide, the starting compounds, and two OH groups connected, eliminates a molecule of water and forms the ketone group. So from a mixture of a compound of more than one compounds, if there is an aldehyde, when you add sodium bisulfite, you get its salt. Then it is water soluble, may be separated, and then it is crystallized, and then it is further treated with the acid so that we get the free aldehyde or ketone. So that can form a purification method for aldehydes or ketones. Now addition of alcohols add to the carbonyl group of aldehydes and ketones in presence of HCl gas. That is important, HCl gas. CROH splits into RO negative and H positive. H positive gets connected to oxygen and RO negative connects to carbon, and we get what is called a hemi acetal. So here OR bond is shown here. OR bonds. OH, OR. Then hemiacetal, hemi indicating half, completes to a full acetal structure by further reaction with another molecule of alcohol, and there OH and H combine and remove water. So minus H2O in presence of HCl gas. So another molecule of ROH reacts and HOH is removed. So we get another OR group, and this is called acetal. So formation of hemiacetal and acetal, it's a characteristic reaction of aldehydes and ketones both. And that forms another nucleophilic addition reaction. Now other reactions are there, we shall see later. Thank you.